Good morning and welcome to Psychiatry Grand Rounds. This morning I have the pleasure of introducing Dr. Matthew McBee. Dr. McBee obtained his bachelor's in psychology at Tennessee Tech University, his master's in educational psychology at the University of Georgia, and his PhD in educational psychology at the University of Georgia. He is currently an associate professor in the Department of Psychology at East Tennessee State University. Please welcome Dr. McBee.
Hello and welcome. Here, can you guys hear me? All right, well, thanks for having me today. It does take a special kind of nerd to come here on a Friday afternoon to hear about statistics, so I feel I'm talking to my people. Today I want to talk about some basic statistical issues and then move into what we've learned in the last few years about how using our existing statistical paradigms can steer us in the wrong direction, and some thoughts on how we can do better. Okay, I guess that's not going to work. Okay, so who here has heard of Bayesian statistics or is familiar at all with the arguments that are happening now between the Bayesians and the frequentists? So for most of us, for myself, and I'm guessing all of you, if you've had any statistical training, you've been trained in the frequentist paradigm, and that is using statistical software like SPSS, Excel, things like that, where you calculate p-values and perform significance tests and calculate confidence intervals and things like that. All those things are part of frequentist statistics, and that's really what I'm going to be talking about today for the most part. There is a whole other worldview, just want to make you aware, in the statistical world that's Bayesian statistics, a different philosophy with a different goal. But in some ways, I think the Bayesian philosophy is more suitable for what scientists and physicians are trying to do with statistics. But we'll talk about that a little bit more. So that's just kind of a background point to keep in mind. But the basic idea that's at the heart of frequentist statistics is this notion of the sampling distribution. And when I'm teaching this, I describe this as the frequentist thought experiment. This is the logic that underlies all of the calculations that get done in frequentist statistics, which is the idea that even though there's only one study, right, you're only typically going to do a single study. The idea is to imagine what would have happened if you had repeated that identical study over and over and over again. Each time you would have obtained a slightly different result because of the influence of sampling error. So the sampling distribution is the idea that if you recorded all of those individual study results from the study that you repeated over and over and over again, what would the distribution of outcomes have looked like? That's the sampling distribution. So with that in mind, there's really some different ways of trying to summarize the result of a study that will give you different information. So you can use the study's data to calculate a point estimate. Point estimate will tell you essentially what was the outcome you observed in your study, right? So when you gave patients an antidepressant, how much did their depressive symptoms change? Or when you prescribed a certain treatment, how did that change the likelihood of survival in the treatment group? So you could calculate that. That's a single number. It's a point estimate. And when that point estimate is expressed in a standardized way, it's called an effect size. We'll talk about that more in a little bit. You can also take that point estimate and combine that point estimate with some information about the sampling distribution to produce what's called a test statistic. And that test statistic is really a way station that takes you to the point of calculating a p-value. And the p-value is, for a lot of us, the first, last, and only thing that we look at when we look at statistical results. But I think that's a mistake, and I'll tell you why in just a few minutes. But to get the test statistic, we would take the point estimate that's generated from the study, which again is telling us like what was the amount of improvement, what was the difference between the treatment and control group in the one study that we looked at, and we could divide that by the standard error, which measures how much variation in study results would we expect to see due to sampling error, and that division gives us the test statistic. And then we can use that test statistic to calculate two quantities of interest: confidence intervals, which measure the imprecision of our estimate, and also p-values, which allow us to do hypothesis tests. So again, test statistics, we take some meaningful point estimate from the data, we divide it by our estimated standard error, which tells us how variable will we expect the results to be due to sampling error, and we get a kind of ratio. That ratio is called the test statistic. And you can think of the test statistic as a kind of signal-to-noise ratio, right? If we observe that subjects in the treatment condition do 5 points better on some outcome, right? But we would expect 15 points of variability due to sampling error, that 5 points of improvement may not be very meaningful. But if we expected much less variability because of sampling error, that 5 points of improvement could be very meaningful. So that's really what the test statistic is trying to measure. It's a signal-to-noise ratio. So the idea is, let's say that we do a study, we estimate, we calculate the point estimate, we calculate the standard error, we divide those things and get the test statistic. Let's say in this particular case, our test statistic is very close to 0, so that's the blue dot there you can see on the axis. Again, in real life we only do the study once, but the frequentist thought experiment says, what if we'd repeated this study over and over and over again? What would have happened? So let's say we repeat the same study again, and the second time we do the study, we now have, I guess this doesn't work. Oh, it has to be on. Okay, there we go. So the next time we do the study, we get a different result. Right? You can see the red dot from last time is there, but now we've got this updated blue dot. So here's a new result. And let's say we do the study again, and we have a new result. And again, if we repeated this many, many, many times, let's see, please. Okay, and we built a kind of what's called a density plot. You know, as these results are being recorded, this curve here is proportional to how often results in particular ranges are appearing. So higher means more frequently. So this is called a density plot. You can see that as more and more studies are done, this density plot's getting smoother and smoother, and it's becoming, it's going to approach either a normal distribution or some other distribution depending on the exact scenario. But the width of this thing, that distribution is the sampling distribution, and the width of it is the standard error. Okay? So then we get into what can we do with this information. What often, as I said, the first, last, and only thing that we often look at when we do this kind of statistical analysis is we use the information in the sampling distribution to perform a null hypothesis significance test. And there's a very rich history of this. This is the basic paradigm for statistics in medicine and social sciences. So generally what you do is you build up a kind of straw man. The logic of this is very difficult to understand, I think, because it has lots of, it's almost like triple negatives. So let's say that you give somebody a new drug because you think that drug will help them. That's what motivated you to do the study, right? But what you're going to do to actually test for that effect is you are going to set up what's called the null hypothesis. The null hypothesis would be, in most cases, the opposite of what you think. So your null hypothesis would be that the drug is ineffective, that it doesn't reduce symptoms or whatever. So then we can calculate a value that tells us how consistent is our data with the null hypothesis. And that's what the p-value is. When you look at an article and it says p equals 0.01, that's what that number is. How consistent is the data in the study with the null hypothesis? So the p-value is the probability of getting the test statistic that you obtained, or an even more extreme test statistic, under the assumption that the null hypothesis is true. So this is why statistics is difficult to teach and counterintuitive to understand. So the idea is You think that the new treatment is beneficial. So you assume that it's not beneficial, and then you calculate a number that tells you how inconsistent is your data with that assumption that the medicine does nothing. And that's what a p-value is. It has at least 2, possibly 3 negatives in its definition. And that's why it's very counterintuitive for people to understand and frequently misunderstood. So if you get a high p-value, p-values are probabilities, so they range from 0 to 1. A p-value close to 1 means that the test statistic that you calculated is very consistent with the null hypothesis. Remember, the null hypothesis is usually that there is no effect of the treatment, that whatever thing you're investigating does nothing, right? So a high p-value means that your data are consistent with that assumption. A small p-value, close to 0, means the opposite. A small p-value means that the data you obtained are inconsistent with the assumption that your treatment does not work. So if the data are inconsistent with the assumption that it doesn't work, what's the only conclusion you can make? Obviously, right? There's 2 possibilities. Either it works or it doesn't work. So if you can say that it's unlikely that it doesn't work, all that's left is that it does work. So that's the logic. Although you're not allowed to say that, actually. That's not allowed. That's a thought crime. If you say rejecting the null means that you have accepted the alternative, no, you can't say that, even though that's the only logical conclusion you can draw from rejecting the null hypothesis. I don't know who came up with this. I didn't come up with that. I'm just telling you the rules. But the p-value is a number that measures how consistent your data are with the null hypothesis. Okay? So the idea is, when that number is small enough, when it becomes sufficiently small, you are likely to say, you know what? I don't believe that this medicine does nothing. Right? When you make that determination that the null hypothesis is not likely to be true, you have rejected the null hypothesis. Okay? So there's another negative. Are we up to 4? Or was that only 3? Not really sure. But rejecting the null hypothesis is what people mean when they say statistical significance. Statistical significance is simply a shorthand for that you've rejected the null hypothesis. Okay? So if you don't reject the null hypothesis, then the proper language, according to frequentist statisticians, is that you fail to reject the null hypothesis. So that's negative number 5, perhaps. Again, if the language here was straightforward, people like me would be unemployed because this would be intuitive and you wouldn't need a stats class because it would just be really obvious what it means. So that begs the question, I guess, of what do we mean by sufficiently small? As I said, when the p-value is sufficiently small, you will, in your mind, abandon your skeptical position, right, that the medicine does nothing, and you will then adopt a position that the medicine does something. So what do we mean by sufficiently small? Well, it's really important that you decide what sufficiently small means before you see the p-value. Otherwise, because of the way people's cognitive biases work, you may be inclined to move your evidentiary standard to wherever the data are instead of making the data conform to some pre-held standard. So that standard for sufficiently small is what we call the alpha criterion. And by convention, it's set to 0.05. So generally, when p-values are smaller than 0.05, we reject the null hypothesis and we say that we've achieved statistical significance. Why 0.05? Bruce Thompson, who's a noted statistician, has said, surely God loves the 0.06 alpha level as much as he loves 0.05. It's arbitrary. Actually, a paper just came out last week or the week before last. It's actually not even out yet. It's a preprint that came out where a group of 70 scientists across different disciplines, including biomedical, have suggested that the alpha cutoff be moved from 0.05 to 0.005. So that's a controversial suggestion, but 0.05 has been the historically conventional standard for alpha. So when p is less than 0.05, we generally say we have statistical significance and we celebrate. Now, so remember I showed you earlier when we engage in the frequentist thought experiment, we get this distribution of different results that could occur, right? And that, I said that was called the sampling distribution. If the null hypothesis is actually true, that sampling distribution is going to be centered at 0. And in this figure, it is centered at 0. And you can see these shaded areas here starting at about 2 on this side and about -2 on this side. So I just told you a second ago that alpha of 0.05 is the usual standard or the usual criterion for statistical significance. So that light shaded area, I've shaded 5% of the area under this sampling distribution. So that's what an alpha of 0.05 indicates. What that means is, so that light shaded area is what's often called the rejection region. When we do the one study that we're going to do and we calculate a test statistic, if that test statistic falls into either this shaded range or this shaded range, we're going to reject the null hypothesis. Okay? Now let's say that this blue line is the test statistic we actually get from the one study that we do. We can calculate, remember I said the p-value is the probability that we get a result equal to or more extreme than the one we actually got. So if I take this, our one single observed outcome, and I shade the area to the right, that's a set of test statistics that are more extreme than the one we got. But I also have to imagine that this result had been the same magnitude but in the opposite direction. And I have to shade on the other side as well. That dark shaded area, if you calculate, if you added up that amount of area under the curve, that is the p-value. So graphically, that's what the p-value is. That probably didn't help anybody at all, but that's what it means. That's intuitive, right? Just put that up there and let's go home. All right. Now, moving into some points that are maybe less well understood. What happens if you did a number of studies, and each time you did the study, you recorded the p-value that you got? Turns out that the distribution of p-values takes on different shapes depending on whether the thing you're studying is actually true or actually false. So imagine that you were investigating a medication that had no effect except for a placebo effect, right? But let's say in your study you're randomly assigning people to your medicine or a placebo. So the control group's already getting a placebo effect as well. So your medicine's no better than placebo. And if that's the case, each time you do your study and you calculate a p-value, if you did that many, many times, the distribution of p-values in that case is flat. All p-values are equally likely. So when there is no effect, when your hypothesis is not true, when your medical intuition is wrong, when your scientific insight is lacking, I'll make this sound great, huh? The distribution of p-values is perfectly flat. All of them are equally likely. You're just as likely to get a 0.01 as you are to get a 0.09. Right? Now, if, on the other hand, your medical intuition is correct and the new treatment is better, or at least different from the old treatment, what you will find is that in that condition, small p-values are much more likely than big p-values. And that's what should happen, right? Since we reject the null when p is small, we would want there to be more small p-values in this condition. So the distribution of p-values looks something like this. So I use the phrase right skewed to describe this distribution. You can see that there's a long tail here pointing off to the right, so that's right skewness. Most of our p-values are in the small range, but we do have some that aren't small. And this becomes important to understand for some reasons we'll talk about soon. Just the other day, Just yesterday, actually, a new study came out in social psychology, which is not my field, but it's a field that I beat up on from time to time. And in this paper, the authors had done 8 experiments, and the p-values they got were 0.05, 0.04, 0.04, 0.03, 0.04. They were all barely significant p-values. That is not something that should happen. That is not something that is likely to happen when there is a true effect. When there is a true effect, you ought to see a lot more very small p-values, 0.001, right, 0.005, than you're seeing these barely significant ones. So when you see that kind of pattern, that should tell you something. And we'll talk in a little bit more soon about what that something should be. Okay, so how do you interpret? What's the proper interpretation of a p-value? Or at least of a statistically significant p-value? People always want p-values to mean more than they actually do. The p-value is telling you something about the data. The p-value is the probability of the data. The p-value is not the probability that the hypothesis is true or false. It's the probability of getting weird data under different conditions. So a significant p-value simply means that the data you got in your study would be unusual under the null hypothesis. And going from that simple statement to a larger statement about inference is actually very difficult. But if you look through the literature, you'll find all kinds of incorrect interpretations of p-values. People will say things like, the p-value is the probability that the null is false. That's not true. The p-value doesn't say anything about the probability of the null being true or false. The p-value is calculated under the assumption that the null is true. And it calculates how discrepant would the data be under that condition. So it's a statement about the data. It's not a statement about the hypothesis. Statistical significance, this is a common misconception, means that the theory being investigated is supported. Not necessarily. There could be other theories that would make the same prediction that the one you're testing. Right? So only in the case where you have a very specific prediction that would be made by one particular theory, but not made by any other theory, would a significant p-value actually mean that. Statistical significance does not mean that the finding is likely to replicate in similar studies. That's not what it means. But it is probably true. And I couldn't write down a proof of this, but I've seen this over and over in the last couple of years. This is my intuition at least. That a p-value of 0.04 is a lot less likely to be seen again than a p-value of 0.001. And that's simply because a 0.04 is not very likely to be observed when an effect is actually present. So there's that, but there's probably no formalization around that. So again, the question that p-values actually answer, or statistical significance actually answers, is what's the probability of the data, or more extreme data, given that the null hypothesis is true? Have any of you ever actually wanted to know that? Is that a question you have? I know when I sit down at a computer to do a statistical analysis, that's actually not my burning question. My burning question is usually, did this treatment work? You know, is this treatment superior to other treatments? Is this finding consistent with some theoretical whatever? What we usually actually want to know is, given the data we have, how likely is the null to be true? Like, we want to start with the data and reason to the hypothesis. And that's actually, like at the very beginning I told you there's a difference between frequentist and Bayesian. Bayesian statistics lets you do that directly. That second point is what Bayesian statistics allows you to do. So in Bayesian analysis, the data are treated as though they are, it's not like you could have gotten a million different data sets. It's like, given this one data set I do have, how can I reason about the probability that these different hypotheses are true? So usually I feel that Bayesian analysis does answer the question we actually have more directly than frequentist analysis. But what's good about p-values? So we've talked about how they're counterintuitive, that hardly anybody understands what they actually mean. that they don't directly answer a question most of us have. What is good about them? And there is one thing they're really good at, and that's error control. So p-values are very useful for limiting our rate of false inference. So how often are you going to fool yourself? If you are studying a drug that does not work, how often will you erroneously conclude that it does work from the data that you've collected? That's what p-values are good at. We talked about the alpha criterion. How small does the p-value need to be before you call it statistical significance? And I said that that's typically set to 0.05, but some people say it should be 0.005. 0.05 in that case would be the rate of false positive conclusions. So if you use an alpha of 0.05, it means you're going to fool yourself 1 out of every 20 times. 5% of the time, you're going to fool yourself by concluding that whatever you're investigating does work, when in reality it doesn't work. So you get to decide, how often do you want to be wrong by choosing a different alpha criterion. That is the one good thing about p-values, and it's a very valuable thing. Again, I said that when the null hypothesis, i.e., when there is no actual effect, when that is in fact the case, p-values follow this flat distribution where they're all equally likely. In that case, 5% of them are going to be in the less than 0.05 range. So those would be times when you would fool yourself, when you would make the wrong conclusion. Okay? Okay, I think I already said all this. That was a good thing about p-values. The bad thing is that they are counterintuitive. Most generally don't answer questions that we actually have. So let's shift away from p-values for a minute. Let's talk about, going back to the very beginning, we talked about how you can represent the results of your study as a point estimate. So how big is the difference between the treatment and control means or whatever? Or how big is the difference in the relative risk of dying for people getting some old treatment versus some new treatment? That is called the effect size. And often the effect size is a much more important thing to consider than simply whether a result is statistically significant or not. So if you think about it, statistical significance at best answers the question, is there an effect or not? It's a yes or no proposition. Right? If physicists operated this way, then we might know that there is gravity, but we might not know how strong it is. Effect sizes are actually what tells us in a numeric way how strong is the effect that we've estimated. Is it very strong? Is it very weak? And so some examples that you've probably seen in the literature are things like Cohen's d's, or number needed to treat, or relative risk, or odds ratios. When you see terms like that, those are effect sizes. They tell you how potent the treatment is, not merely whether it has an effect distinguishable from zero. Okay? Now, effect sizes are point estimates, but there's uncertainty around those effect sizes that can be expressed using a confidence interval. Confidence interval is a range of values that are broadly compatible with the result we got. So here's an example of a table. Now this data set actually comes from, it's a built-in data set in the R statistical software. And the data set is called Viagra. So I don't know the details here. I know that what's being compared is a high dose of Viagra versus a low dose of Viagra versus a placebo. I don't know what the outcome variable is. I could guess. Maybe you can too. And I don't know what a 5 means on whatever scale they were measuring. But anyway, so here there's 3 arms in this study. And what you have So for each group, you can see that the high dose group, the outcome has a mean of 5, a standard deviation of 1.58. Low dose has a mean of 3.2, and the placebo group had a mean of 2.2. Okay, so this column right here, this 1.24, is a Cohen's d effect size that's measuring how different is the high dose group from the low dose group. And the metric is in standard deviation units. So what that 1.24 is an effect size, and it's telling us that the high dose group is scoring on average 1.24 points higher on the or 1.2 standard deviations higher on the outcome variable than the low dose group. Now that's typically considered to be a large effect size. At least in the social sciences, anything over 0.8 is considered to be large for most circumstances. So that would be considered a very big difference. A very strong dose-response kind of relationship here. But then look beneath it. In brackets, what we have here is the 95% confidence interval around that estimate. And the width of that, every number inside the confidence interval, is a plausible value for what the true effect of this drug is. So look how wide that confidence interval is. It's centered at 1.24, but it goes all the way down slightly below 0 on one end. And it goes all the way to almost 2.6 on the other end. So it's an extremely wide confidence interval. So what that's telling you is, if you simply fixated on this effect size of 1.24, you are failing to realize how much variation there actually is around that number. That many, many other effect sizes are plausible values for the true difference between low and high dose Viagra, including a difference of 0. 0 is in that confidence interval, right? So it's really important, I think, when you estimate or when you interpret effect sizes, to have some sense of how wide these confidence intervals are, because in this case, the result, 1.24, looks really impressive. Wow, that's one of the strongest effect sizes I've ever seen. But then when you look at the confidence interval, you see that it's so wide that you don't really have very much information about the true difference between high and low doses of this drug. So that's really important. The confidence interval gives you a sense of how precisely estimated was the effect size. In this case, the answer is not precise at all. And that's true for all the other effect sizes here too. This one is the difference between the high dose and the placebo group. It's even larger. So if this was estimated with high precision, it would be like the strongest effect ever observed, or something like that. But look how wide its confidence interval is. I mean, it ranges from almost nothing to twice the largest effect ever observed. So this study is not very informative. Right? An informative study should give us precise estimates of these things, and this one didn't. In general, what's going to help us get those precise estimates would be a big sample size. So this study, in this data set, there's only 5 people in each group. And that's why these confidence intervals are so wide. So that's really important to keep in mind. Now, the worst thing about p-values, besides the fact that they're hard to understand and they don't answer directly a question that most of us have, remember I said the best thing about them is this error control property, where they can limit the chance that you're wrong. The problem is that property is very easy to defeat, depending on how the researcher has behaved. So you see this phrase, sometimes researchers' intentions matter. There's something called p-hacking, which is one of several what are called questionable research practices. Questionable research practices are those things that are sort of moral, ethical gray area. They're not fraud, per se. Some of these things that are under the umbrella of questionable research practices can be done legitimately in some circumstances, but when over-engaged in, they can break the error control property of p-values. If you think about the context in which a lot of us are doing research, there are strong incentives to be right, right? There's strong incentives. Things like getting your work published. A lot of journals are not particularly interested in publishing null results. Although that is scientifically valuable, I think. If you investigate some new treatment for depression and that treatment doesn't work, that ought to be published, I think, so that other people know this is a dead end. But the reality of our current publication system is that that probably won't be published. So you did this study for nothing, right? You're not going to have something to put on your CV. It's going to be just wasted effort and resources from your point of view. Things like grants. It's hard to get grants without a publication record. It's hard to gain prestige as a scientist if your whole career is publishing things you were wrong about. It's not really how prestige works in science. It's hard to get a job or promotion or tenure without a solid publication history. And selective publication is what I meant by journals really want to publish positive results, not null results. We have a very competitive academic culture, particularly in biomed. Biomed is insane in terms of how competitive it is. There's not a lot of rewards for getting it right. There's a lot of rewards for getting it first. This is not just the philosophy of Dale Earnhardt. In academia too, there's no reward for being second to discover something. You're just the first place loser. A paper that came out in 2012 by Begley and Ellis. This is published in Nature. They took 53 landmark studies in cancer biology. This is the basic science stuff that you could build drug development off of. 53 studies. I think on average they've been cited over 150 times apiece. They were published in some of the top-ranked journals in the area. You can see that the lowest ranked, I don't know if this means anything to you, but a lot of these were published in journals with impact factors greater than 20. So those are the biggest top journals, Science, Nature, and so on and so on. So this was a set of studies that were influential, had been published in the best journals. They tried to reproduce the results of all of those studies in their lab. They were only able to reproduce the results from 6 out of 53 of those landmark studies for a replication rate of 11%. Now in the paper, it's very interesting to read, and it's very short. I would advise, if you're interested, to just, there's no paywall on this, so you can read it yourself. They describe contacting some of these original labs, and they said, hey, we're trying to replicate your analysis that was published in whatever. And the original authors would say, oh man, we couldn't get that to work either. We had to do that like 7 or 8 times before it worked. So how is it possible, if people are using statistical tests, which should have only a 5% chance of producing a false positive, that we end up in a situation like this, where the majority of the literature is not reproducible? Well, I said the error control properties of p-values are really easy to break. A new classic paper in psychology came out in 2011 titled False Positive Psychology. Undisclosed flexibility in data collection and analysis allows presenting anything as significant. And in this paper, Joe Simmons, Leif Nielsen, and Yuri Simonson did a simulation where they analyzed the effects of many practices that I know are common in psychology, and I'm guessing are common in medicine as well, though I don't know that. But things like, let's say that you measured not 1, but 2 different outcome variables. So maybe you have 2 different ways of measuring depression if you're investigating some sort of a depression treatment. And you will run your analysis on both outcomes. But you will only report the one that works. You will not report the other one. So that's sometimes called selective reporting. Another thing people do So that breaks the error control properties of p-values if you do that, because that 5% is, assumes that you're only doing one test. If you're now doing two tests, that 5% rate starts to creep up. Another thing people do is interim data analysis, or what's called optional stopping. So you might collect data from 50 subjects, run the analysis. If it's significant, you might write up the results and publish it. If it's not significant, you might collect a little more data and try again. If that doesn't work, you might collect a little more data and try again. If that doesn't work, each time you do a repeated test on a slightly different data set, remember I told you under the null hypothesis, all p-values are equally likely, so it's like a random walk. That p-value will at some point walk down below 0.05, and you can say, hey, discovery. So they looked at other situations as well, including control variables in the analysis, or dropping conditions. So maybe you were looking at a study with 3 or 4 treatment arms, but you only see a difference between 2 of those 4 arms. When you write up the analysis, you may fail to mention that there were 2 other arms in the study. You may only report the part that worked. And all those things taken together break the error control properties of p-values. And in their simulation, what they found is that if you start with an alpha criterion of 0.05, in other words, only 5% of all your conclusions should be false positives. When all these techniques are used together, the true false positive rate that they found was close to 61%. Now again, maybe people in medicine are more trustworthy than people in psychology, which I wouldn't dispute, but there was a survey done asking a large, I think close to 2,000 psychologists, like how often do you engage in these different behaviors, which are called questionable research practices. And some of these things were alarmingly common. Things like failing to report all outcome measures was at 78%. Collecting more data after seeing whether results were significant, 72% of people admitted to doing that. But there's even some things that are really scary. Falsifying data, 9% of people admitted to doing that. And things like rounding p-values. People do this. They'll get a p-value that's actually slightly above 0.05, then they'll round it down. Like, oh, Yahtzee, it was significant after all. 39% of people reported doing that, rounding down p-values. So again, p-values have all these problems. The one virtue they have is error control. But the sociology of how our fields are organized, the incentive structure, the reward structure that faculty and researchers face, pushes us very hard towards doing things that violate the one virtue that p-values actually have. So I think time is running out. This is supposed to end at noon, is that right? Do we want to leave some time for questions and discussion? I have a few more slides I can do, but I'm also happy to stop here and we can talk about this. What do you guys want to do? I can do. Okay, all right, I'll do that. So, given that this is the case, what should you trust? There's a movement now to require or at least encourage researchers to do what's called pre-registration. So pre-registration simply means that researchers, before collecting their data, they produce some sort of time-stamped document saying, here's what my study was. Here was my design. Here were my outcome variables. Here were the arms of the study. Here was my analysis plan. And the point of asking people to document that in advance is so they can't change their plan once they have the data. So when you see a study that is pre-registered, I think that will make the results much more likely to be true, that you should invest more trust in pre-registered studies. Now what's interesting is before the year 2000, clinical trials that were registered through clinicaltrials.gov were not required to be pre-registered. And what you will see is that here are all these dots. Each dot represents a clinical trial. A black one, there's actually a little plus sign in there you probably can't see. That's a trial that reached the conclusion that the treatment being investigated was helpful. And the blue ones are inconclusive. And red ones mean the treatment was actually harmful. So before pre-registration was required, there was a very high rate of clinical trials yielding claims of efficacy. 2000 comes along, and due to change in federal policy, clinical trials now have to be pre-registered. Look what happened after pre-registration was required of clinical trials. Most clinical trials failed. Only 2 in this figure were able to generate positive claims of efficacy. So that kind of begs the question, what about these over here? How many of those things are real? Or how many of those claims were reached through p-hacking? So again, I already touched on this. When people engage in questionable research practices, the effect is to convert what would have been a non-significant result to a significant result. But when that happens, the results tend to be barely significant. So this is an example of a Twitter post from a few months ago where, teaching a highly prestigious article from 2008, and the p-values are 0.045, barely significant, 0.09, not significant, 0.05, right on the cusp of significance, maybe had actually been rounded down to significant, 0.02, 0.04, 0.04. When you see a pattern like this, where a set of results are close to the boundary of significance, that is not a good sign. In fact, you may want to take the paper, wad it up, throw it away, and do not update your own priors based on this information, because this is not likely to be true when you see this kind of pattern. Another thing that happens, because of publication bias and these questionable research practices, there's an interaction between study size and effect sizes. When you see a small study that claims to have a very large effect size, you should be extremely skeptical of that claim. I've seen this taught wrong in stats textbooks, including one that our department had adopted, where it said something like, oh, if you see a really big effect size in a small study, that must mean that the thing is extra true. But that's not how it works. It's actually the opposite of that. When you see a large effect size from a small study, you should immediately at least suspect that that large effect size has been dramatically inflated, that the true value is probably much smaller than what's being claimed. And here's some examples. In social psychology, again, I got to beat up on it. This is an embodied cognition study where the original claim is that when people wash their hands, they did not judge others' moral transgressions as harshly. It's like somehow washing your hands has this metaphorical value that changes the way you think about transgressions. So here's the first claim. First claim published, an effect size close to 1. Very big effect size. But you also notice those lines coming out from there showing you how wide the 95% confidence interval is. It's quite wide. And that's because that original study's sample size was 27. If you were just going on that original claim, you'd be like, wow, we discovered this really powerful new part of human psychology. That's really amazing. But then, look what happened when replications occurred. Another research team did the same study with a larger sample size, close to 300. Look what their result was. Much narrower, and actually in the opposite direction to the original claim. So after doing several replications of different sizes and things like that, down here at the very bottom, this is an aggregated confidence interval over all of the replications. You'll see that it's sitting on 0. There is nothing in here. I'm pretty confident when I say that washing your hands does not make you judge other people's moral transgressions in some different way. The first study claimed that, and they claimed it was a very strong effect. Here's another one. Similar idea, embodied cognition. 2 studies come out claiming huge effect sizes based on samples of 51 and 41. And then look what happens. A set of pre-registered replication studies was done. Much larger sample sizes. and we integrate over all those, nothing. Okay? And here's another example. Effect of mood on helping. First study, small, based on N of 41, big claim. Again, what's the phrase the kids are using nowadays? Nothing burger? This is a nothing burger. Another one. So, what's the takeaway? I'm going to skip ahead to Ioannidis is a biostatistician. Things that you should keep in mind when you're reading the research. Small studies, less likely to be true. Right? Be skeptical of small sample sizes. The weaker the true effect of something is, the less likely the findings are to be true. I'm just going to skip a couple of these. I think the last point's really important. Well, the fourth one and the fifth one are really important. Number 4 says, the greater the flexibility in design, definition, outcome, and analytic mode, the less likely research is to be true. There's some areas in psychology where there's over 200 ways of measuring the same idea. My guess is that there's not a lot of truth value to a lot of claims in that area. That's just me. Number 5, the greater the financial and other interests and prejudices, the less likely research findings are to be true. That speaks to the question of incentives. The more strongly people are incentivized to produce statistical significance, the more likely they are to do it. Because p-values are easy things to break. So that's something to keep in mind. And that's the last of my slides. So happy to entertain questions or discussion.
Would you want to comment on the importance of differentiating effect size interpretation from tabular asterisks in terms of levels of p-value significance?
Yeah, thank you for asking that. That's a great question. So oftentimes when you read research and you skip to the results section, you see the tables where the statistical results are presented. You will often see that people will use differing numbers of asterisks to indicate how significant their p-value was. So maybe 1 star means it was p less than 0.05, and 2 stars might mean it's p less than 0.01, and 3 stars might mean something even more. People often misinterpret that. The size of the p-value does not tell you how strong the effect is. Right? That question is answered by the effect size, and more importantly by considering the effect size in combination with the confidence interval around the effect size. So those are two different things. So you'll hear people say things like, oh, this effect is really, really significant. And that's not what... it is true that when you see a very small p-value, that indicates perhaps more likelihood that the finding could be observed again in another study. But that doesn't mean anything about how big the true effect size is. It could have been a very weak effect, but in a very large sample. That would also generate a very small p-value if the claim is actually true. So thanks for that question. Yes?
The way that faculty are treated in terms of explaining how they get paid by a drug company for something. We're required, as you, I don't know if you had the slide, to divulge any money that you may have received from a drug company or anything. Those things are really tiny compared to the financial benefits to the faculty member from just their job alone, getting grants, their prestige. Those are huge incentives that affect research. And the little tiny things that we are forced to report have virtually no influence because they're, by comparison, they're very small contributors to the income of a faculty member. So when we sit here in psychiatry, and I think all medical grand rounds have the same requirements, and two people give a speech, and one person has to admit that they did a talk for a drug company and received an honorarium, and that somehow would influence people's opinion about the data, when in fact the second person, who doesn't divulge any of those things, works at a major research private institution whose salary is dependent on providing, lots of positive findings and high impact journals. So it's very, the way that we have, the way that administrative arms at universities have handled this is so contorted, and I wish that they would come here and listen to this and understand that what motivates people to do the things that you showed on that graph is not, getting pencils and pens and little gifts from drug companies. That's not what causes people to make those decisions. They make those decisions because they need to get positive findings. They know that for their livelihood, period. It has nothing to do with the little trinkets.
Yeah.
That's just
I used to work at a research institute that was completely funded by soft money. Everybody there was supported by grants, and it was exactly like that. I mean, there was a lot of good stuff coming out of the institute, but everybody there was under immense pressure. You had to constantly be getting grants. If you couldn't get a grant, you were done. You were fired. I mean, that's how you paid for your own salary. So, and what facilitates that? A publication record. I mean, being right. It's the whole process. It's the whole thing. Right. I agree. I think a massive cultural change is required at universities, publishers, different incentives, or ultimately what it's going to take. We have to stop incentivizing people from doing bad things if we want the quality of science to improve.
Thank you, Dr. McBee.
Thank you.